Welcome to Maths with EJD. In this video, I'm still looking at numerical solution to initial value and boundary value problems. And now our focus turns to Runge-Kutta fourth order method for initial value problems. So like I said earlier, so we have ordinary differential equations, otherwise known as ODEs, and they are classified into initial boundary value problems. Initial value problems and boundary value problems. Initial value problems have initial conditions, something to start with, and then you have boundary value problems. They have conditions at two different ends that your equation has to satisfy. And for initial value problems, we have two methods. We have many methods that can solve them, but we are concentrating here on Euler's method, and of course, Runge-Kutta method, Runge-Kutta method. Then for boundary value problems, we have we have the finite difference method. Finite difference method. So we first encountered finite differences when we talked about numerical differentiation. So finite difference is also useful here, finite difference method. And then we have what is called the shooting method. Shooting method, another method for solving boundary value problems. So far, we have dealt with Euler's method, and our focus now turns to Runge-Kutta fourth order method. So Runge-Kutta methods. Okay. Now, the Runge-Kutta methods are a family of iterative methods used for solving ordinary differential equations, ODEs. Okay. The most common one, it's a family, right? So it means there are many of them. So the most common one is the fourth order Runge-Kutta method, also known as RK4, fourth order, right? Which is a more accurate, it's more accurate and efficient approach, than simpler methods like Euler's method. So Euler's method, the advantage of Euler's method is that it is very simple, easy to implement, but it is not quite as efficient as this other one. Now, the RK4 method computes the next value, yn plus 1, by evaluating the function at multiple intermediate points within the step, making it significantly more accurate. Just like we saw under Euler's method, right? If you want higher accuracy, you need smaller step sizes. And smaller step sizes would mean more computation time. So it takes more energy to do smaller step sizes, but you get better results. So the formula for the RK4 method, is yn plus 1 equals yn plus h over 6 into k1 plus 2k2 plus 2k3 plus k4. So that's the formula basically. But then it doesn't end there. All those k and everything actually has a significance. They are significant, that is. So where k1, so that k1 now is basically, if you remove all the other k's, everything becomes like Euler. So where k1 is equal to the function of xn, yn, and then k2 is f of xn plus h over 2 yn plus h over 2 k1. So you see this one depends on the k1 you would have done previously. Then you go to k3. So k3 is f of xn plus h over 2. All right. Xn plus h over 2, comma, yn plus h over 2. The k2 you get up there, you bring it down here. Then you have k4, which is f of xn plus h finally, xn plus h, and that is yn plus h k3. So now you see that in all these formulas, in these formulas, in these formulas, h is the step size. H is the step size, and f of x comma y is the function defined by the differential equation. Okay. So that we can compare our results here with what we got from Euler's method, I like us to solve the same problem. So let's talk about an example, the same example. So here, solve dy dx equals x plus y with y of 0 equals 1, that's the initial condition, over x in the interval 0 to 2. Exactly the same problem like we did previously. So let's go for this. Solution. So first thing, we want to solve, so we have our differential equation, dy dx equals x plus y. We have the initial condition, y of 0 equals 1. We have the interval, x belonging to the closed interval 0, 2. Then so you have to decide on the h you want to take. So if you're not given h, you can decide. So let's take h to be 0.1. You can take it to be anything, but as far as you're not given, so you can take it to be 0.1. So the function itself that we want to work with, right? The function f of x comma y is actually x plus y. That's the function itself. So that's going to help a lot of things. So we define the function like that. So the first thing we want to do is to initialize. So initialize initialize. So to initialize means we have the initial condition, that is y of 0 equals 1. That implies that x naught is equal to 0 and y naught is equal to 1. So that's the starting point. So with that, we can go on. So the next thing is we want to compute the first few steps, I mean, because of how tasking this can be, I may even do only the first step and then move on to the code, because it's a lot of work trying to do I mean, if you want to put everything together. So let's look at this now. So it means we need to get K1, K2, and all the rest. So look at K1. K1 is just like Euler's method. So we can now go. So now what we need is we need from the overall formula, we need yn plus 1. So now that we have x naught, y naught, so we now need the first iteration. First iteration is y1 equals y naught plus h over 6 into k1 plus 2k2 plus 2k3, then plus k4, I believe. Yeah, I think that's what that looks like. Yes, up there. So now we need k1. So we just go k1 is f of x naught, y naught. Okay. So k1 is f of x naught, y naught. And the function itself is defined as x plus y. So that's x naught plus y naught. So that means k1 is simply x naught plus y naught. That is 0 plus 1. Based on the fact that we already know x naught plus y naught. X naught is 0, y naught is 1. So k1 is equal to 1. Settled. Then we go for k2. So k2 is f of xn plus h over 2, yn plus k2 xn plus h over 2 plus yn plus h over 2 k1. So the k1 we got up there is going to be useful for k2 also. So think a better color code to make it easier. So now we have k2. Okay, k2 is equal to, generally, k2 is f of x naught, x naught plus, let's say that again, k2 is x naught plus h over 2 plus y naught plus h over 2 k1. Okay, x naught plus h over 2 comma y naught plus h over 2 multiplied by the k1 up there. Okay, I think that works. Yeah, x naught plus h over 2, y naught plus h over 2 k1. So let's put that together. So I mean, let's sort this out so we can easily put the values later. Or better still, if we follow the same pattern, K2 will just be whatever we have here. So since it's x plus y, right? So we just have x naught plus h over 2 plus y naught plus h over 2 k1. So that's like x plus y, basically. So that k2 now is equal to x naught is 0, h is 0.1 divided by 2 plus y naught is 1, h over 2, that's 0.1 divided by 2 multiplied by k1, which is 1 that we got the other time. So k2 now is equal to 0.1 all over 2 plus 1 plus 0, 0.1 all over 2 again. That's 0.1 all over 2 because multiplied by 1, it remains the same. So K2 is equal to 0.05, I believe. Yeah, that's 0.05. Then plus 1 plus 0.05. Okay, so that we now have K2 to be 0.05 plus 1.05, 1.05. So that is like 1.10. So K2 is 1.10. So we need this K2 for the net for K3, if you remember. So K1 is 1, K2 is 1.10, right? And then we need K3 now. So I go for K3. So again, K3 is equal to f of x naught, okay, plus h over 2, comma, y naught plus h over 2 plus h over 2 multiplied by the k2 we just got up there. That's how that works. Okay, so we now have k3 to be, since f of x comma y is x plus y, so this is just x naught plus h over 2, all right, plus y naught plus h over 2 k2. Okay, so that K3 now is equal to 0 again plus 0.1 divided by 2 plus y naught, that is 1 plus 0.1 divided by 2 into K2. K2 now is 1.1. K2 is 1.1. Okay, so we have K3 to be equal to 0.1 divided by 2 plus 1 plus okay, 0.1 times 1.1 is basically 0.11. You just shift it forward. 0.11 over 2. So K3 is equal to 0.05 here plus 1 plus 0.55, I think. That should be 0.55. No, 0.055. Okay, 0.055. So K3 now is equal to 0.05 plus 1.055. So this can be quite tricky. That should be 1.155 or something like that. Or 1.105. Let's say 1.055, then 0.05. So this is 5, this is 1. I mean, this is 0, this is 1. So 1.105. 1.105. So K3 now, K3 is K3 is 1.105. Okay, that's K3 right there, 1.105. So we still have K4 to go. So for K4 now, so K4 is a bit different from the rest. K4 what's K4 now? K4 is xn plus h, not over 2 now. Xn plus h, yn plus h, K3. Okay, so K4 is equal to function of x naught plus h plus y naught plus h K3. Okay, so that K4 now, like I've been doing before, I could just say x naught plus h plus y naught plus h K3. I could say that since f of xy is simply x plus y. So this would now be like my x and this is like y. So I could just add the two together. But this time around, I'm not going to go that way. I'm going to take another approach. So you can know that you can now do it in another way. So what I'm going to do here is, first of all, get the values of those things before adding them up. So that means I'm just going to have f of, as we know, x naught is 0, h is 0.1, okay, comma, y naught y naught again is still 1, right? Y naught is 1. And then we have plus h again is 0.1. And K3 is what we just got. That's 1.105. So this is 1.105. That's K3. All of that here. So we have K4 now equals the function of 0 plus 0.1, that's 0.1, comma 1 plus 0.1 times 1.05, 1.105, that's 0.1105. Okay, so that K4 now is equal to f of 0.1, comma 1.1105. So K4 is a function of that, and it means that we can then add the two together simply. So K4, since K4 the function f of xy is just x plus y, so we have 0 plus 0.1 0.1 plus 1.1105. So K4 now is equal to 1.2105. So this is our K4. Now, with all that done, we have got K1, K2, K3, K4. With all of that done, we can then update Y1. If you remember, we can update Y1. That's where we're coming from. Y1 now. Y1. Y1. So we want to update that. Don't forget, Y1 is simply this expression right here. Okay. So we update Y1, which is actually Y naught. I mean, Y1 is equal to y naught plus y naught plus h over 6 into K1 plus 2K2 plus 2K3 plus K4 now. All right, so we can update that. So y1 is equal to y naught is 1 plus h is 0.1 divided by 6 into K1. We got that to be 1. 2K2, that's 2 into K2. 2 into K2, that's 2 into 1.1 plus 2 into K3, which is 1.1 105, 1.105 plus K4, which is 2, which is 1 actually. We can shrink this a bit. So that is 1.1105, I believe. Yeah, yeah. K4 is 1.2105, sorry. 1.2105. 1.2105. So y1 now is equal to 1 plus 0.1 over 6 still into 1 plus 2.2 plus 2.210, I think. 2.210. So that is 2.21, then plus 1.2105. So that y1 now is equal to 1 plus 0.1 over 6. To make things easier, you could call that 1 over 60. If you multiply top and bottom by 10 rather, into all this now is 6.62, which is 6.6205. 6.6205, because 1 plus 2.2 is 3.2. Then 3.2 plus this is 5.41. Then 5.41 here is 6.6205. So that works. Then y1 now is equal to 1 plus, so if you 6.6205 times 0.1 over 6, so that's simply going to be all of that is 0.11034. So finally, we have y1 to be up to be 1.11034. Okay, that's what y1 end up being. So we can say thus y of 0.1 is approximately 1.11034. Okay, that's what that should be. So, I mean, if you are doing it in a tabular form now, just like I like to go, you have, imagine that you have I here, then you have xi, and you have yi. Okay, so, I mean, you can go on and on and on, following the steps, but I mean, that'll be a lot of stress. So I'm going to just go for the Python code. So far, we have I is 0 and we have I is 1. Those are the two we have right now. So X naught, you remember, is 0, Y naught is 1. Then now, X1 is at X1, that is 0.1. That's because 0.1 is the step size. Then Y1 is what we just got now. That's 1.11034. Okay. So, I mean, if you want to follow my perfectionistic tendencies, you could just say 1.00000 if you like, just to make sure the number of decimal places are the same. So with that done, right, you can go for the second iteration. All right. So, but I mean, I won't bother, just like I said already, but I want to just talk about that briefly. So so second iteration, which I'm not going to do, by the way. So in that case, you see that x1 is equal to 0.1. Y1, you already have to be 1.11034. So you're going to use that. To get y2. You will use that to get y2, which is now equal to y1 plus h over 0. Plus h over, what's that now? Yeah, plus h over 6, sorry. H over 6 into K1 plus K2, K1, K1 plus 2K2 plus 2K3 plus K4. And this time around, K1 is going to be f of x1, comma y1 again. So K2 is going to be f of x1 plus, how does this go? That I think that's h over 2. That's how it usually is. Yeah, that's k over 2. Yeah. Then we have Then we have H naught. I mean, Y1 now. Y1 plus H over 2, the K1 up there. Then K3 is going to be F of X1 plus H over 2 again. Then Y1 plus H2 K1. And lastly, K4 will be F of let me see. Okay, X naught plus H, Y naught plus HK3. So this will be X1 plus H, X1 plus H, comma Y1 plus HK3, like that. So, and that's how all of that will go. So you just evaluate this at the end of the day. All right. So mm, we can then say that this process, this process can be repeated for each subsequent step, for each subsequent step until uh until we get to x equals 2, following the steps, following the fact that h is 0.1. But of course, because how tedious the manual implementation can be, we have the Python implementation as usual. So this is the Runge-Kutta uh fourth order method, that's RK4. Oh, okay, let me make it start fresh. Okay, so I mean, look at it here. So in lines 5 and 6, you define the what you're solving, that's x plus y. Then here we have the um, exact solution. Thankfully, if there's no exact solution, we won't be able to do this. So you can just go ahead and find other ways of estimating the error. So we have the exact solution right there. Yeah, I think I made a mistake in the last video about the exact solution. I didn't represent it quite well. The exact solution is actually 2e raised power x minus 1, not 2e raised power minus x plus x minus 1. No. So let's work on that. I think I put it in the comment section on YouTube to correct that. All right. So here, we now define RK4. That's what you have here. So the Y values, we have all of that here. X naught, and then we keep incrementing by that H value. Then we have the Y values, which take the values of X, and Y value 0 is Y none, which is the initial condition. Then we define the Ks, we define all the Ks this way. Okay. And finally, you see our Y1 here. So you see the H that should be out here over 6, we already have each of the H in all of these places. So we don't have to worry so much about those ones. Okay. So at the end of the day, we now have so we just run this. We run this and then we get our results. So you see, this is for 0.00, we have 1.000. For 0.1, we have 1.1110,342. And we have 0.2, and it goes on like that. So we can do up to 2, all these steps. And then you can see in this case, as opposed to the Euler method, you see that everything matches perfectly. So because Runge-Kutta method is more accurate than Euler. So you see, we have that working so well here. So in the case of Euler, you still had some from the beginning they are together, and then as the steps increase, you have that departure, and that's why Runge-Kutta is usually preferred um to Euler. So we have this like this. Now, this process, okay, I mean, we already said that this process can be repeated. We've seen how the code can help us. Now, let me show you the end of Euler method that we did. So you can use this same method now. We have some practice questions you can deal with. I'll just project them briefly. So you can use, probably you've used Euler for this. So you can now go ahead and use Runge-Kutta. Use RK4 now method with step size h equals 0.2 to approximate y equals 0.4 for the IVP. You can do that. So it means you're doing up to 3 steps or something like that. Then you are going to solve this using the So now if you have used if you have you can use Runge Euler, then use Runge-Kutta. Now that's RK4 now. Okay. Then this one also find the exact solution and compare the results with RK4 approximations. Okay, that's Runge-Kutta fourth order. Hope I'm not moving too fast. So I mean for this now, this question three, consider the differential equation that with the initial condition. So compare, I mean, you do it with Euler, now do it with RK4. Then the fourth question, given the y dx equals all of this, apply Euler's method with h equals 0 to approximate that. So now you can apply RK4, also Runge-Kutta fourth order method with h equals 0.1 to approximate this. Then compute the percentage error if the exact solution. So you are given the exact solution, so you want to compute the percentage error like that. Then number 5, you can approximate y of 1 using Euler's method with h equals 0 to for the equation dy dx equals 3x plus 2y, y of 0 equals this. So now you want to approximate using RK4 after using Euler. So you can easily compare and see which one converges faster. So that's how that has been. And then we're done with the Runge-Kutta fourth order method. So we are done with the Runge-Kutta fourth order method, and that's how that goes. All right. So if you have not subscribed to this channel, go ahead and do that. And if you have subscribed, thank you so much. Don't forget to hit the notification bell so you can always get alerted each time a new video is released. And comment, let me know how helpful these videos are for you. And let me also know if you need me to teach a topic or solve a problem, I might be able to find time to do all of that. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.